Hello and welcome to Group 12's video presentation for the ES3C2 Advanced Mechanical Engineering Design module.
The aim of our project was to design a complete rear suspension system from the ground up, optimized for a racing application using a double wishbone configuration. This involved developing all key components ourselves, including the wheel, tire, hub, brake disc, and wishbones. We also had to select appropriate brake calipers, bearings, and design constant velocity joint to ensure smooth power transmission. From hand calculations to CAD modeling and final integration, every decision was made with motorsport level performance in mind.
For our design, we were given one of the most challenging sets of parameters. Our vehicle had a total mass of 270 kilograms, including an additional 80 kgs for the driver mass. In addition, we were assigned a coefficient of friction of just 0.95, which meant reduced grip for both longitudinal and lateral forces. This required us to be especially precise in managing weight transfer and traction to ensure performance and safety. The lower grip and greater weight also put additional demand on component selection, braking performance, and structural integrity. To ensure safety and performance, we had to conduct detailed weight transfer calculations.
Starting with the static load, each rear wheel supports approximately 640 newtons. However, under dynamic scenarios, the load increases significantly. During acceleration, we calculated a rear wheel load transfer of 1400 newtons, whilst braking produced a rear transfer of 1330 newtons. Lateral load transfer during cornering reached 1368 newtons. In terms of powertrain performance, we determined a peak torque under acceleration of 340 newton meters, which corresponded to a maximum acceleration of 7.64 newtons per second squared.
For our wheel assembly, we specified 6-inch rim width, an offset of 30 millimeters, and 3 lug hole configuration. To create our model, we traced cross-sectional images of braid wheels, which were provided to us, and used those profiles as guides to our rim geometry. The two diagrams shown here are the cross-sections we used during modeling. We also applied the designated tire thread pattern, completing the assembly to match the project requirements.
For our braking system, we selected a brake disc radius of 110 millimeters. This size ensures adequate clearance within the wheel while also providing the maximum achievable braking torque within the packaging constraints. We evaluated two caliper options, the AP Racing CP4226 and CP4227. Ultimately, we chose CP4227, which features dual pistons on each side, offering improved clamping, force distribution, and better thermal performance. We employed a hat-shaped brake disc design, which features the usage of two materials for increased mass reduction. The cutouts made enhances heat dissipation by allowing more efficient airflow. For the brake pads, we compared AP420, RQ3, and RX compounds. All options exceeded our required torque. However, we selected the AP420 pad due to its progressive braking characteristics, which support smoother corner entry and better modulation.
The wheel hub acts as the central connection between the suspension upright, the drive shaft, and the wheel. Calculations were completed to ensure that our stress values were within our chosen material of medium carbon steel. The final equivalent stress came to 117.6 newtons per millimeter squared, which was within our limits of 177.8 newtons per millimeter squared. We began with the SKF 61815 bearing, but its static load rating was insufficient. An angular contact double row bearing was next, but too bulky to accommodate. Finally, we selected a single row tapered roller bearing with a 75mm bore. This design balanced compactness with load bearing capacity. We validated our bearing design using standard equations.
The upright is a key structural component that connects the upper and lower wishbones, hub, brake caliper, and drive shaft. It's responsible for transmitting all loads from the wheel into the suspension system while maintaining alignment. In our design, we focus on maximizing stiffness to prevent unwanted deflection, which is key for predictable handling. At the same time, we ensure the structure was robust enough to meet safety requirements and endure real-world suspension loads through our calculations. We began the design by selecting the inner and outer bearing axis lines as our main datum features. Revolving the geometry around these lines gave us a strong foundation for symmetry and accurate placement of all mounting interfaces. From this base, we carefully constructed the upright using reference edges, bearing center projections to ensure proper alignment and structural clarity. The final design integrated all major suspension mounting points, which included the upper and lower wishbone pickups, which handle vertical and lateral loads, the tolling interface, which allows for fine-tuning of steering angles, and the strut rod mounts, which manage longitudinal loads during braking and acceleration.
Wishbone calculations were done to determine members that were under tension and compression. The maximum force was also calculated to ensure that failure modes are accounted for. The tolling experienced the greatest force, and such the calculated length was sketched up in CAD for modeling.
The final part left to design was the adapter for the constant velocity joint. This connection allows the CVJ to connect with the rest of the wheel assembly. The overall design exhibits 6 drilled holes in the wheel hub for 8mm diameter dowels, and M8 screws are used to fix the adapter to the CVJ.
Our final CAD assembly integrated all components while managing space constraints, structural stress, and manufacturing feasibility. Major challenges included fitting bulkier bearings and maintaining shaft integrity. Design trade-offs were carefully evaluated to balance performance, safety, and manufacturability.